Welcome back to the Deep Dive. Today, we're opening a file that, frankly, feels like we stumbled onto a briefing from the future.
It really does have that vibe, doesn't it? The document's titled State of the System, Part 4, and right at the top, the dateline says 2026 briefing. It feels a bit like we're reading something we aren't supposed to see yet.
Exactly.
Yeah.
And the topic. It's arguably the heaviest hitter in the history of physics. We're looking at a slide deck, a technical visual breakdown of the island formula and the resolution of the black hole information paradox. Now, I know that sounds like a mouthful of jargon, but my understanding is that this is the mission brief on how we fixed one of the biggest breaks in our understanding of reality.
That is not an exaggeration. For about 50 years, physics was effectively broken. We had this massive, glaring contradiction where black holes seem to just delete information from the universe, which breaks the fundamental laws of quantum mechanics.
Right.
But this deck, this is the solution. It visualizes how we went from a paradox to a proof.
Okay, so our mission is to decode this thing. I'm going to walk through these visuals, which are beautiful, by the way, very sci-fi wireframe aesthetics.
Yeah.
And you're going to help me understand what on earth we're looking at.
I'm ready. It's a dense journey, but the destination is, well, it's worth it.
Let's jump into slide 1. We've got the title, The Island Formula, but the visual sets a very specific tone. We've got this wireframe sphere, which I assume is the black hole.
Correct. That's the system.
Okay, so inside this sphere, floating deep in the center, is this glowing blue geometric shape. It looks like a 20-sided die, an icosahedron or something. And shooting out of it, punching right through the sphere, is this beam of binary code that explodes into a cloud of particles on the outside.
It's a perfect opening image, that geometric shape inside that represents the island. And that beam of data shooting out, that represents the recovery of information. The whole point of this deck is to explain how that beam can possibly exist. It's the journey from, confusion to mathematical clarity.
Okay, moving to slide 2, we get the backstory. It says the Island Formula 2019 breakthrough. So this is recent history. It credits 2 groups, Geoff Penington at Berkeley, and a team listed as Almheiri, Engelhardt, Marolf, and Maxfield.
Right, usually called the West Coast and East Coast teams. And what's wild is that they arrived at the same conclusion, basically simultaneously. They provided the first rigorous proof of the page curve.
I keep seeing that term, page curve.
Yeah.
The slide says it represents the preservation of information. Why is this curve the holy grail?
Okay, so imagine you're watching a library burn down. If you stand outside and collect the smoke and ash, the radiation, at first it just looks like chaos. The entropy or disorder just goes up and up and up. That was Stephen Hawking's original prediction.
The curve just goes up and the information is lost forever. Okay, so Hawking said the library is gone, vanished.
Right. But Don Page, another physicist, said, no, if quantum mechanics holds up, eventually you should collect enough ash to start reconstructing the books. The curve should go up, but then it has to come back down to 0 once the fire's out. The Page curve is that hill up and then down. These teams prove that gravity actually follows that curve.
And the key to that proof is in the definition section here on the slide. This is where it gets weird. It says an island is a region deep inside the black hole. But then it says, at a specific moment called Page transition time, this interior region mathematically becomes part of the outgoing radiation.
This is the part that usually breaks people's brains.
Yeah, I'm struggling with it. I'm looking at the diagram on the right. You've got the singularity, the future horizon, and the shaded blue island. There's an arrow connecting the island deep inside to the radiation far outside. It calls this connection the entanglement wedge.
Think of it this way. We usually define inside and outside by location. If you're behind the event horizon, you're inside. You're stuck. But this breakthrough redefines location based on entanglement.
Entanglement is that spooky connection between particles, right?
Yes, exactly. What this proves is that when a black hole gets old enough, the deep interior becomes so heavily entangled with the radiation outside that it stops belonging to the black hole. Mathematically, it is the radiation.
Yeah, so it's teleportation. The slide uses the word teleported.
In a sense, yeah. The information isn't traveling through the space in between. It's more like the ledger for that region moves from the inside column to the outside column.
Wow. That is a massive shift in how we view space. But this leads us to slide 3, which tackles the problem that made all this necessary. The firewall paradox.
Firewall. This was the nightmare scenario before the island formula fixed it.
The slide describes the paradox as a conflict with the monogamy of entanglement. Now, usually when I hear monogamy, I'm not thinking about subatomic particles.
Which sounds like a relationship advice column, But in quantum mechanics, it's the rule that a particle can only be fully entangled with one other thing at a time.
Right. You can't have two spouses.
It's a surprisingly accurate analogy, though. In quantum mechanics, a particle can only be fully entangled, let's just say married, to one other particle. It's strictly monogamous.
Okay. So where's the scandal?
The scandal is that an outgoing particle leaving the black hole needs to do two things. First, to save the information, it has to be entangled with the radiation that left a long, long time ago. It has to correspond to the old data.
So it's married to the past radiation.
Right. But general relativity, Einstein's theory, says that space has to be smooth at the horizon. For that to happen, the particle also has to be entangled with its partner that just fell into the black hole.
So it's trying to be married to the partner inside and the partner outside at the same time.
Exactly, and quantum mechanics forbids that. It's called polygamy of entanglement, and it's impossible. So physicists thought, well, the bond with the inside partner must break. But breaking a quantum bond releases energy, a lot of it.
A firewall.
A literal wall of fire at the event horizon. It meant that if you jumped into a black hole, you wouldn't float in. You'd get vaporized instantly. It completely broke Einstein's theory.
But the slide says the resolution, the island formula, proves no dual entanglement. How?
Look at the visual under the resolution. You see the island circle and the radiation circle merging.
It says the island is the distant radiation.
That's the trick. The particle isn't cheating, isn't married to two different people. Because the island on the inside and the radiation on the outside are mathematically the same thing, the particle is just entangled with one entity that we're viewing from two perspectives.
So there's no polygamy because the two partners are actually the same person.
Precisely. Yeah. And because there's no conflict, there are no broken bonds. No broken bonds means no firewall. You'll just be crushed into infinite density.
Right. But it's nice to know physics isn't fundamentally broken.
But I want to know why this happens.
Slide 4. The mathematical mechanism.
Why does the universe decide to hand over the keys to the interior? The mathematical mechanism, minimizing entropy.
This is the engine under the hood. This is why it's not just a nice story, but a mathematical necessity.
We've got a scary-looking formula here. Break this down for us without making our eyes glaze over.
It looks complex, but the logic is actually beautifully simple. It's based on the rule that the universe always tries to minimize generalized entropy.
Okay.
So when we calculate the entropy of the radiation, the math has to hunt for the configuration that gives the lowest possible number.
Okay, low entropy. We like efficiency. The universe wants to save energy.
And the slide breaks it down into two phases. First, we have early times, the green phase.
And it says no island.
Right. When the black hole is young, the island region is empty. The entropy just grows linearly. This is because the pile of radiation outside is just getting bigger and bigger, and it's all entangled with the black hole. The math says the simplest way to describe this is just a growing pile of junk.
But then we hit late times, or page time, the blue phase.
This is where the magic happens. A new saddle point appears in the math. Suddenly, it becomes mathematically cheaper or lower entropy to include this island region in the calculation.
So it's like a switch flips. The universe realizes, hey, if I include this chunk of the interior as part of the exterior, the total entropy goes down.
Exactly. It minimizes the total entropy. And because the system must follow the path of minimum entropy, the island suddenly pops into existence in the calculation. It's not a choice, it's a requirement. Let's look at slide 5, the dominance shift, because this visualizes that switch perfectly. We have a graph with a big X on it.
This is the famous phase transition.
Okay, so we have a green line going up, forever labeled Hawking's prediction, and a purple line starting high and going low labeled island calculation. And the system follows the thick blue line that traces the bottom of the X.
That's the minimizing rule in action. At first, the no island calculation is lower, so the system follows that line up. But at the crossing point page time, the lines cross. The island calculation becomes the cheaper option. So the system just snaps to that track and starts going down.
It mentions the quantum extremal surface, or QES. Is that the switch?
The QES is the edge of the island. When that surface appears, it's the signal that the universe has switched to the new calculation. It acts as the wedge that forces the transition.
Okay, now slide 6 gets into the geometry of this switch. Path integrals and replica wormholes. The visuals here are distinct. Topology A is called the Hawking saddle and looks like two disconnected tubes. Topology B is the replica wormhole, and it looks like a funnel or an hourglass connecting the top and bottom sheets.
This is where we get into how the island connects to the outside. The path integral is a technique where we sum up all possible histories of the universe. We look at every shape space-time could take.
Okay, so we're auditing the universe's shape.
Yeah. Early on, those disconnected tubes are the dominant shape. But later, these replica wormholes become the preferred path.
It looks like a tunnel bridging two separate worlds.
That's effectively what it is. As the black hole gets older, these wormholes become the path of least resistance. The slide says, as the wormhole saddle shrinks, it crosses from outside to inside the horizon. This is the geometric bridge that lets the interior be identified with the exterior.
Slide 7 calls this the principle of least action. It asks, why is this natural?
This connects back to classical physics, which is really cool. The slide mentions optics like Fermat's principle, where light always takes the quickest path, or statistical mechanics, where systems move to the lowest free energy.
So this weird wormhole stuff isn't some new magic. It's just the universe doing what it always does, finding the path of least resistance.
Exactly. But look at the implications section. This is the heavy part.
Yeah, it says, space-time is fundamentally non-local.
That's the pill you have to swallow. To accept the island formula, you have to accept that a region deep inside a black hole is topologically linked to radiation millions of miles away without anything physically traveling between them in the normal sense.
And there's a catch listed here, too. It says this relies on Euclidean path integrals or imaginary time.
Yes. The math works perfectly in imaginary time, which is a mathematical tool we use. But as the slide notes, there is an ongoing debate. Are these wormholes real physical structures, or are they just accounting tools that happen to give the right answer?
So the math says the wormholes are there, but we aren't sure if they are there.
That's the frontier of the research. But the fact that they solve the paradox suggests they're capturing something very real about the structure of space-time.
Moving to slide 8.
Competition in moduli space. And the visual is this three-pronged wormhole structure.
It looks like a futuristic subway map.
This represents moduli space. That's the space of all possible geometric configurations. The slide tells us that the existence of the island implies that the moduli space of quantum gravity is highly entangled.
It mentions replica symmetry and taking n to 1. This seems like the heavy machinery of the math.
It is. Briefly, to do the calculation, physicists imagine n copies of the universe like parallel sheets. They connect them with these wormholes, do the math, and then take the limit as n goes back to 1, just our universe.
Wait, so we pretend there are multiple universes to fix the math for our one universe.
It's a standard trick called the replica trick. By creating those extra copies, we can see connections like that quantum extremal surface that are invisible otherwise. It's like using a shadow to figure out the shape of an object.
Got it. So we have the map and we have the wormholes. But slide 9 asks the practical question, reconstruction. The question is, how do we actually get the info out?
Right. It's one thing to say the data is safe. It's another to say we can actually read it.
The slide lists the PETS map.
So what is a PETS map? It sounds like something you buy at a gas station.
It's a mathematical filter. Imagine you shredded a document, but every shred was mathematically linked to a specific location in a cloud of smoke.
Okay.
The PETS map is the algorithm that tells you which shred corresponds to which puff of smoke.
The slide explains that for any operator deep in the bulk, that's the island, there is a corresponding boundary operator in the radiation.
It says the mapping. For any bulk operator O sub I, there exists a boundary operator O sub R.
That's the translation key. It proves that the island is a sub-region of the radiation's code subspace. If you have the radiation and you have the PETS map, and granted, a wildly powerful quantum computer, you can reconstruct exactly what fell into the black hole.
You can reconstruct the interior particle just by looking at the radiation cloud.
So if I collected all the Hawking radiation and ran it through this PETS map algorithm, I could reconstitute the encyclopedia that fell in.
Theoretically, yes, though the computational power required would be astronomical. We're talking about a computer larger than the universe running for longer than the age of the universe. But in principle, the data is there.
We'll need a bigger computer.
Slide 10 deals with temporal non-locality. The visual here shows a swirling grid labeled island on the far left, connected through a vertical horizon barrier to scattered dots on the right labeled radiation. But the labels also say distant past and outside future.
This addresses the time aspect.
The island formula shows that the island connects the interior past to the exterior future.
So the information thought to be lost in the past is actually encoded in the radiation collected far away in the future. The island connects the interior past to the exterior future. It's showing that the information isn't just teleported in space, it's bridging time. Information we thought was lost to the past is actually encoded in the future radiation.
That leads perfectly into slide 11, the Kachi Horizon Information Recovery. We have two contrasting images. On the left, a blue shifted flash, a blinding wall of light. On the right, the island, a stream of data penetrating that light.
The blue shifted flash is the old nightmare. It's the singularity or mass inflation. In the old physics, this was a wall at the end of time. If you hit that, your information is just scrambled and destroyed.
But the slide calls the island the loophole.
Exactly. Because of that non-local entanglement we discussed, the information doesn't have to smash into that wall. It bypasses the singularity entirely. The flash is the wall at the end of time. The island is the loophole, allowing information to survive it.
We're getting into some wilder territory now with slide 12. Multi-island scenarios and platonic symmetry. We have a glowing blue star shape, an octahedron or icosahedron again.
This asks, what if the black hole is really, really complex? Specifically, if it has BPS platonic symmetry.
And the geometry partitions into multiple islands. It says this creates accelerated saturation.
Think of it like parallel processing. Instead of one big connection, you have this lattice of many connections, like a crystal. This allows the entanglement to work faster. It drops the entropy curve more steeply.
And horizon fragmentation. The horizon has discrete symmetric hotspots, so it's not a smooth black sphere anymore.
In these highly symmetric states, yes, it becomes a structured geometric object rather than a featureless void.
Slide 13 talks about black hole stability. We have two states, pure BPS and near BPS.
BPS stands for a specific condition in string theory. A pure BPS state is visualized as an infinity loop. Mass equals charge. These are eternal. They don't evaporate. They last forever.
Versus near BPS, where mass is greater than charge, the visual is a decaying curve.
These are the black holes we've been discussing, the ones that evaporate. The slide notes are risk of decoherence from environmental dirty matter or destabilization at page time.
Right. The intricate wormhole connections we've been discussing, they are delicate. They rely on precise quantum entanglement. In a transient state, incoming matter, dust, gas, cosmic rays could disrupt that entanglement.
It raises the question, does the island formula hold up in a messy, dirty universe, or only in a pristine mathematical one?
Exactly. We need to know if these wormholes are robust enough to survive the chaos of the actual universe.
But that instability is exactly what allows them to radiate and give the information back.
All right, let's bring it home. Slide 14, summary, state of the system. We have three colored boxes.
This is our wrap-up. Green box. Resolve, the paradox is solved. The island formula proves the page curve works using gravity. Blue box. Mechanism. It's driven by a phase transition in the path integral. We switch from Hawking saddles to replica wormholes. Pink box. Structure. Space-time is non-local. The interior is a code subspace of the exterior.
Slide 15 gives us a glossary and definitions. I'm just going to run through these rapid fire to cement them for our listeners' mental bank. QES. The minimal surface acting as the boundary of the island. Page time, the half-empty point where the dominant shift happens. Moduli space, the space of all geometric configurations. PETS map, the tool for reconstruction. BPS state, mass equals charge, extreme stability.
That's a solid toolkit for anyone wanting to dive into quantum gravity papers.
You know, going through this, I feel like my view of the universe has shifted. We tend to think of space as this rigid container. Things are here, or they are there. But this document, it says that here and there are just options. That space kind of creates itself out of entanglement.
That is the deepest lesson here. Space-time isn't the stage the play happens on. Space-time is the actors holding hands. So after 4 episodes, after all this math, what does this all mean for us?
It means that the universe is far more interconnected than we perceive. We look at a black hole and see a dark pit where things disappear. But if you look with the eyes of quantum gravity, if you look at the entanglement, you see that the inside is actually the outside. You see that space can fold and tunnel to preserve information.
It means that space and time are emergent, doesn't it?
They are the projection of the entanglement. The connections create the space, not the other way around.
Listen, I want to take a moment to thank you.
Yes, thank you. Your dedicated attention is what makes these deep dives possible. We know this stuff isn't easy, but understanding it gives you a glimpse into the fundamental operating system of reality.
Absolutely. Go let your brain cool down, maybe stare at a wall that isn't a holographic projection. Or is it?
Don't start.
Thanks for listening to The Deep Dive. We'll see you next time.
See you next time on The Deep Dive.